look at this picture where we said, well, imagine I want to implement this process where I give you some system which is near criticality, or just thinking about a phase transition in some magnetic system. And what we wanted to ask was, what happens to this system if I kind of look at it by doing this process of decimation, where I'm removing some number of degrees of freedom and asking about the leftover degrees of freedom, but looking at it at larger length scales. Okay? And we did this, in some ways, in exactly implemented in the case of the 1D Ising model, and then some way of implementing this in the 2D case, which was much more hand waving, right? And what we want to kind of, what I want to do today is kind of ask, what do we learn from this hand waving thing? I mean, it's clearly a procedure which, I don't trust, right? But is there something useful to take away from there that we can then kind of start asking questions about the physics in the vicinity of the phase transition? So let's kind of very quickly kind of go through this, the end result that we got for this decimation process, or this thinning out degrees of freedom in real space that we did for the Ising model in the 2D case. And what we did crudely was the following, and there are other ways to do this which I will mention in a second. But one way to do this, which we said, was to take this approximation where I'm going to kind of simply by hand deform some of these bonds. So this problem kind of looks like a problem which is a bit more like the 1D problem of Ising chains, along certain directions. So all these sites are spins, right? And we said, well, we can kind of reduce it to a problem where, at least for these spins, they only couple to two neighbors, and it's very easy to, get rid of them, or actually sum over these spins and sort of compute some effective Hamiltonian for the remaining degrees of freedom. Right? And so we went from here, and we went through this whole process where we kind of ended up with spins now that live only here. And then we said, well, that's not good enough. I also want to do it in the other direction. So finally, we went through a process of moving and decimation, a second step here, where we ended up with spins that now live on only these sides, right? So there's a couple of steps here that I'm kind of skipping here while drawing this. But we went through this entire process last time, and we ended up with something where if I started with some exchange interactions measured in units of temperature was K in this case, then here it would be some new exchange, let's say K twiddle. Okay? And what we had was an expression for K twiddle in terms of the original K. And for this particular complicated process, we ended up with something which, let me write down the expression we had. So we had this 1/4 log of hyperbolic cosine 4K plus half log cosine. So if we start from here, we could say, well, we found that this allows, this equation in principle has, 3 fixed points and not just 2. The Ising model, in some sense, in one dimension, had just 2 fixed points. One was unstable, which was that if I'm at 0 temperature and I go to any non-zero temperature, it would flow away to the infinite temperature point. This equation we saw last time allows for the possibility that I have 3 possible fixed points, one of which is at K going to infinity, one of which is at K going to 0. But there's a third point here at some value of K star. Okay? And if we look at how this, if we kind of just iterate this in the vicinity of these 3 points, we find that the system kind of flows, this particular K kind of flows along this line in the following fashion. Okay? And one way to see this then is to say, well, let me try and look at this equation at large K and see that K tends to increase under iteration. we can look at it at small k and just kind of Taylor expand this and see that it shrinks under iteration. But there is a third point k star, and for this particular equation, k star happens to be, some number which is like 0.43 or something, roughly. But this third fixed point, unlike these two, is unstable, which means if I now take a point which is k star plus delta k, right, and ask how delta k changes under this iterating this equation, then we find that the new delta k at the next step, this distance delta k is given by some number which is roughly 1.63 times delta. Sorry, this is some approximation. So imagine I'm sitting at delta k that's positive. So if I start here, then at the next step, the distance from that point k star will grow. It will get multiplied by this factor. So it's going to grow and it's going to keep getting bigger, right? If on the other hand, I start with delta k on the left, then this delta k twiddle at the next step is going to be larger again, but it'll be negative, right? And so you're going to kind of keep marching towards the left. Okay, so this is an unstable fixed point. Okay, and this unstable fixed point we can now kind of associate with the phase transition itself, right? So we had these two stable fixed points where the k going to infinity was the ordered phase. This here was the paramagnet. So this was a phase that was a stable fixed point, and the unstable fixed point we will associate with a critical point of the Ising model in 2 dimensions, or in this particular case, on the 2D square lattice. Is this fine? Okay. So what do we learn from here? We learn that this coupling constant or this exchange interaction is growing in a very certain way. So if I repeat this twice, so if I kind of go from delta k, I would go to some, let's call this some number g or something, right? So this will go like some g times delta k. And if I iterate it again, this will go like g squared times delta k, and so on. Okay. And at every time when you iterate this, your length scale is basically changing by a factor of 2. Right? The distance between these points, when you go from this to this, the length scale has changed by a factor of 2. If you repeat it again, it will become a length scale, which is 4, and so on. Okay. And so now what you can try and kind of take away from here is that certain quantities in the vicinity of this fixed point will kind of behave as some power of a length scale. So I can associate this g, right? So this g, was some number here which I wrote down, so 1.63, and I can associate this with some 2 to some log of log to base 2. Let me just write it as some, b to the power of some alpha. I'm going to give it a name later, but let's just call this some b to the power of, trying to find some name here that I'm not going to use later, but okay, let me use alpha. This alpha is not the critical exponent alpha for the specific heat that we wrote down earlier. Where this is going to be my length scale. Sorry, this is not what I wanted to do. So this, we can think of this as, delta k at the end of certain number of steps is going to go like, b to some power, and we'll kind of define what this in a second, times the delta k in the initial where this is the amount by which the length is changing each time, right? So if I have gone to, some number of steps, this will be some, let's say this is, n steps. Then this will be some b to the power of n. Sorry, this is not also what I want. Sorry, just 1 second. I'm trying to write it in this form that I want at the end of the day. Sorry, I just want to write this as sorry. So B is the factor by which the length scale is going to change. Let me not do this way. So let me write this delta K in 1 step. Maybe I should call it log to base 2 of this 1.63. Okay, so this is the amount by which the length scale is changing. And if you change by this particular length scale, there's a certain power of the length scale by which this constant is changing. So let me not use alpha and various other things. And I can keep repeating this, right? And so what you're going to get if you repeat this is that if you do this many times, then this is of course going to go like 2 to the power of, if I repeat this n steps, then you're going to get some n times log to base 2 of this number here. And let me I'm just writing down this approximate number from this particular value times delta. This is after n steps. Yeah. So. Which one? That's what this is, right? No, this is not empirical. This is what we calculated. So we calculated that this is the recursion relation. With this recursion relation, if we demand that k twiddle should be the same as k, right? That's the fixed point, right? And that's satisfied. If k goes to infinity, then this is satisfied. If k goes to 0, then this is satisfied. Okay. But if k goes to some special value k star, then also this is satisfied as an identity, where the left and right hand side are equal with k twiddle and k both being k star. Right. The next step we said was let's make a small deviation away from this fixed point, right? And let's say that deviation is delta k. And now I'm going to iterate this equation. So I start here, I put in some delta k, and I ask what is the new value of k twiddle and how far is that from the fixed point? Correct. So if I choose a certain value delta k, then this is some multiplicative factor times delta k, right? And now I'm rewriting this as a power of a length scale. In this case, the length scale is changed by a factor of 2 raised to some power, right? I have not done anything really different at this point, right? But here, if we kind of iterate this equation once more, then we'll say, oh, delta k double twiddle, let's say, right? Is going to be the square of this number times delta k. It's basically going to be this number is now going to be multiplied by 1.63. You're right. I think so. If we look at how these scales flow, if I'm a large scale or small, can I say that in different directions? So there might be a point where it does not flow at all. This is K star. Correct. How do I, without knowing K star, do this sort of figure out that okay? I think how do I do a Taylor expansion like the kind of that mapping near K star? Because only then can I sort of come up with something like this, right? So I know Taylor expansion about correct. Then I see that the linear term survives. That's what I'm worried about. And should the linear term survive? Why should we start with delta k square? It could, yeah. So you could have examples, and we'll kind of see this later, that there could be examples of what something where the linear term vanishes, and those will be kind of marginal things later on we'll see. Okay, so there are examples where it need not have been just a multiplicative factor. Here, multiplying delta k, it could have been something proportional to delta k square. right? So it's not obvious, but I'm just saying in this case, if you go through it, this is what we find. Yeah. Okay. Sorry. Yeah, in this particular, okay, sorry, maybe I'm not, okay, we can sort of come to exactly what the changes that I need for looking at something that's, so you could have something that's marginally irrelevant, for example, where it could be proportional to delta k square, and eventually you make a small deviation, and it very slowly flows back to where you started from. It's possible that that happens. Sorry, was there something? Yeah, so you can get things that are, somehow that look as if they're not flowing to order delta k, but they will flow at some higher order, and then in which direction they flow, you have to work out sort of the coefficient that tracks how big, what are those changes. Yeah. Okay. So in this case, the main point was that under this iteration, this distance is going to blow up exponentially as you keep doing this more and more times. It looks kind of like every time I should be multiplying by this factor that's bigger than 1. Okay. And so every time the distance is increasing by the same factor each time. Okay. And if you do that, then you see that after n steps, you are at this point, which is kind of very far from where you started. And that means you've kind of flowed to a point which is very deeply in the ordered phase or very deeply in the disordered phase. Yeah. Okay. And so now you can say, well, does this, what do I learn from here? So we've learned that, in fact, that this thing is an exponentially growing distance, right? Or if you think about sort of the number in the exponent, then this thing is kind of growing linearly with the number of steps equivalently, right? If I write it as a prefactor, it's kind of growing with the power of the number of steps. Or if I write it in this exponential form, then this exponent here is kind of changing with the number of steps. Okay. So let's say that we try and do this differently, this whole decimation process, and ask, well, what changes in this entire thing? So we could do this decimation process in a way that looks somewhat simpler, but I don't like it as much, but we can kind of do this, is to say, well, let me do this in a somewhat simpler way, which is to say, well, let me take this square lattice, and you can come up with your own favorite prescription for how best to do this. Let's say I have these spins here. And I could, of course, also choose to do this decimation differently, where I say, well, I'm just going to take all these bonds connecting to the spin and just move them to sort of this bigger bond here. So I'm going to erase these bonds. Sorry, let me not do it here. Let me do it here. I'm going to erase all these bonds and just double the strength of the bonds here. Right. And now we can kind of do this by saying, well, I can now just completely ignore the spin at the center because it's not doing anything. It's not coupled to anything else. So when I compute the partition function, it will give me some factor of 2, right? But other than that, I'm going to calculate this as if I'm going to do the decimation like this, where this k here in this step has become 2k. And now I'm going to kind of integrate out these spins because they look kind of as if they're only connected to 2 neighbors, exactly like here, right? And I can do this, and I find that, okay, the equations look slightly different. So in that case, k twiddle turns out to be, 1/2 some log hyperbolic cosine of 4k. So this equation looks different from the one we started with. Okay. But what is common to both of these is that you still find that if I take this equation and iterate it, right, again, you find that, okay, I have something which qualitatively resembles this. I have some k star whose precise value is different. And again, I find that there are these flows. And in this particular instance, sorry, maybe I'll write here. In this particular instance, k star turns out to be, let me just write down the numbers here so that. So K star turns out to be something like 0.3, some different number, 0.30 or something. Okay. And this multiplicative factor is also different. So delta K twiddle turns out to be some other number times delta K, which in this particular case is not too different. It's something like 1.68 times delta K. Sorry, I hope you can see down here. So it's roughly this. So you'd say, well, what I found is that, okay, maybe the detailed numbers are different, but at least there is some idea that if you kind of do this in many different ways, then you can come up with your own favorite way. What you find is that these interactions change in some way. And the way they change is kind of through a multiplicative factor each time you do this iteration. Yeah. Okay. So let's use this and ask, can we learn anything about the system if we kind of imagine doing this more generally, not for this particular Ising model, not for this particular set of interactions K in this case, or this Ising model J that I had. But let's imagine that I have a more general system, equilibrium, I'm thinning these degrees of freedom, changing my length scale by some factor B, where in this case B was 2. I changed by a factor of 2 going from here to there, the length scale. We can ask, is there a more general thing that I could do? And you'd say, well, imagine I were to write down the free energy density of my equilibrium system, right? This free energy density will be some function, and you could do this in Landau theory, or you could think of some microscopic model if you wish. This free energy will be a function of some parameters. And those parameters in this case happen to be just one number, K, right? More generally, we could have done this. Maybe we would have to keep like a magnetic field, right? So there'll be some parameters here where, it could be some, let me call this some, I don't know what I'm calling it in my notes, but let's see if yeah, so I'm just using Landau theory type notation. So let's say there is a field H. Let's say there is some version of something that's this reduced temperature, little t. Okay. Then in Landau theory, we had this fourth order term, which came with some coefficient u. And you could put in more. You could put in sixth order terms. You could put in gradient terms. So there are things like the stiffness. There were things like, you could put in higher order terms. So there's a whole bunch of coupling constants on which the free energy will depend, or the free energy density in this case, little f, right? And that's what we want to do now, is to take this system. Let's say this is on some scale, okay? And now I want to imagine doing this process. We're not going to do this process yet, but imagine doing this process and asking, well, what happens to this process if I zoom out and look at it at some other length scale? Okay. And what we learn from here is that, well, if you look at it at some other length scale, then what you're going to get is that you will still get some similar model that looks very similar, right? Except all the coefficients or these coupling constants, like for example, K in this Ising model, have all changed by some scaling factor. Okay. That's not necessarily true for all of them, right? I mean, but we'll kind of see that this is a useful way to kind of think about the problem, and then we'll kind of justify it a bit as we go. Okay, which is to say, imagine each of these went to some new values, H prime, P prime, U prime, etc., which are related to the original values and by how much you've actually scaled out. Okay. But the other thing that's changed is the length scale has changed, but the length scale has changed while the free energy itself is not changing, right? So we're saying the total free energy is not changing. And so in fact, I have to multiply this by some factor. And if we change the length scale by a factor B, here B was 2. But if I change the length scale by a factor B, then this will go to some B to the power of minus D times the free energy density on the other side, okay? Or the free energy per degree of freedom that you have left. And the way to think about this is, imagine I have a system where I started with something which was defined on a system which has, let's say, sorry, I'm trying to do this as if it's a square. Okay. Let's say it's 4 boxes on a side, right? And let's say that this system has, let's say it has some lattice constant that's, let's say, 1, and it has some length, let's say that is L. I'm drawing it as 4, but it has some length L. And now we are going to go from here to a system where we are going to remove a bunch of these spins, and we're going to end up with a problem where I have far fewer degrees of freedom left. So let me kind of draw it as if that's kind of the leftover stuff. This has now become B, and there are now L by B degrees of freedom left along each direction. And so you have, so many spins here, whereas here we started with L to the D spins. Here we are left with some L by B to the power of D spins. Okay. And what we want is, what we're looking at is kind of the free energy per side, but the total free energy we want is the same in the two cases, in the initial problem and the final problem. So what we want is to say that, well, in the initial problem, if I had some total free energy F, then this is, L to the power of D times some free energy density. Right? In the final case, this same F, we are going to describe by saying I have some L by B, I have some thinned out degrees of freedom times some new free energy density. And so the two free energy densities are related by this extra factor of B to the minus D. Okay. Okay, so this is one where we did not specify what these new parameters are. And we could have done this for any problem at all, right? At any point, we could have kind of said, well, I'm going to, sorry. Yeah. Oh, actually, do you know the value of the J over T critical for the 2D Ising? I don't remember the number offhand, but maybe Sanjeev has access to Google. So, so correct. So okay, so there are two things we want to get right. Okay, one is, what is the location of this? So you're right that, the location of this K star, in some sense, location of K star tells me the location of J over T critical, right? And if I invert that, I'll get a value for TC for the 2D Ising model, right? And so if K star is 0.3, then the critical temperature is about 3, roughly, right? Here, K star was, I forgot, K star was 0.43, critical temperature will be like 2.5. I'm not sure which is closer, but Sanjeev may know. .6. Okay, so maybe this is a little bit closer in that case. It's not very, I mean, the reason that, there are two things we have to get right. One is to say, well, I want to get roughly the correct transition temperature. The second is to say, well, I want to get the right behavior of this, which will become clear in a second. And that turns out to be quite bad for both of these approximations. Okay. Right. So that's the problem which I'll kind of come to in a second, which is that, we can kind of take away from here some general message. Okay. But the point is that there is no clear systematic calculation here, right? I mean, both these are some strange calculations, and we may not trust one or the other, and there's no reason to trust one or the other, right? And in particular, you could come up with some completely different scheme where you say, well, what I'm going to do is I'm going to do this bond moving where I delete these 4 bonds. But sorry, I'm just going to draw it here, right? I could come up with some completely different scheme where I say, well, I'm going to delete just in this problem, delete these bonds, and maybe throw away that spin, but end up with something where I move the coupling constant somewhere else, right? I do something like this. I'm going to take these bonds and I'm going to shift them so that these 2 bonds somehow give me an effective interaction between these two spins rather than the original square lattice spins. You might say, well, that's some very different. It still has the symmetries of the square lattice, but it's some completely different way of doing the problem. And now you see that, oh, this looks like completely weird, and it's a very different setup. And maybe there is some way to kind of make progress along this. I have not tried this particular example. But what I'll tell you is that there are many different ways of doing this decimation process or this renormalization process. And it's not clear at all a priori, what's the correct way or, what's the better way. I mean, forget correct, right? Can we even estimate, which one is better, having no ideas of what the exact results are? And there really isn't a nice way to kind of choose or systematically improve upon it in some way. So this was J by KBT, yeah. 0.45. Okay, so it's pretty close to this particular answer in this instance. Okay. Okay, so we can kind of write down the exact results or something, but here it will turn out that this one is kind of quite a way off from the actual answer. Okay, so we can take this, to some extent, maybe this scheme is better than that, but these answers are actually way off anyway. Correct. So that's the other thing, which is here we ended up, we had some nearest neighbor on a square, but this model looks weird already in the middle step, right? Also, there is no reason for, imagine I did this in the spirit of Landau theory, where I say, well, I'm going to write down all symmetry allowed terms in my free energy functional. Then in principle, if I take the only symmetry of the Ising model is that there's a global Z2 symmetry where all spin going to minus spin is allowed, is kind of a symmetry of the problem. Then we could also write down models as additional couplings here, which are, let's say, second neighbor Ising interactions, third neighbor Ising interactions. We could have written down interactions which are not necessarily two spin interactions, which would involve interactions between four spins at a time. So it could be an interaction that is like S1 times S2 times S3 times S4. That also has the right symmetry, right? So as Shovan was saying, there is no clear picture that the Hamiltonian that you end up with after you do this process should look similar to the old Hamiltonian, right? Or has the same number of interactions or the same type of interaction. Okay, so in principle, if you start doing this, slightly different way of doing this or do it on slightly different lattices, you might find that the resulting Hamiltonian you get after one step looks like nothing like the old one. And then the question is, what do I do next, right? So how do I then proceed? Okay. All right. Any other questions? Okay. So with this, let's now take away from this just one. Yeah, sorry. Think that we should avoid that case. Well, we could possibly find the most easiest way that we just get by not doing what we should. Oh, what to avoid? Correct. So you could, for instance, do something silly where I say, well, I'm going to shift all these bonds down here and get a set of decoupled 1D chains where I will not have any transition at all, right? So maybe, yeah. So somehow one thing to preserve might be, the symmetries of the problem. That if you start with a square symmetry, you end up with a square symmetry. So maybe the square lattice doesn't end up breaking into 1D chains or something. But other than that, it's not very clear what. So I wanted to actually, I had planned to do one thing which I'd kind of skipped, but maybe I'll mention it towards the end where, there's a slightly different problem where, people have done this kind of real space renormalization group, successfully in a much more complicated setting where you take quantum spins on a 1D chain with strong disorder, right? And there is a somewhat more justified way of how to do this decimation by saying that, well, I'm going to remove bonds that are kind of strong because those are kind of high energy degrees of freedom, right? And maybe I'll kind of mention that towards the end. But so there are cases where in some cases you can actually do this even for complicated looking models. You can kind of do this analytically or on higher dimensions. I think you have to do some numerics. But there are ways to kind of justify it in certain cases. Yeah. Okay. All right. So with this, I mean, this seems quite general. This is saying that, I'm going to take my original set of coupling constant. There's an infinite number of them. And you could have written down as complicated a lattice model as you wanted to, or you could have written down a Landau theory with an infinite number of terms, right? And after you remove some degrees of freedom, you're left with some degrees of freedom, which share the same symmetries as the old problem, the Hamiltonian. So you can say, well, there is still an infinite number of interactions and magnetic fields, whatever, right? All of this. And the only thing now is that you realize that, okay, I have left out some degrees of freedom. So the free energy has to stay the same. I have to get this factor of b to the minus d, where d is the dimension. But you can ask, well, can I learn something more than that about how these parameters change when you do this, going to a larger length scale, right? And in that particular case, we can take some inspiration from here and say that, well, at least in this case, these parameters went by something that was related to some power of, the length scale that you started with, right? So it went as some, in this particular case, we went by a factor of 2 to some power, where b was 2. Oh, sorry. Oh, sorry, say again. Are you talking here? Okay. Yeah, so this I'm saying is b. No. Correct. That scaling is coming from here, right? That it's some related to some length scale raised to some power, right? Or you could have taken, okay, you could have taken cell, well, it's some exponential, right? I can always take this and you say, well, why not e to the power of something as opposed to 2 to the power of something? But it's convenient to say, well, if I start off with some length and I do this, let's say length, well, those are the number of, in some sense, if you did this with a different length scale, that would have appeared here, right? So if you, if you eliminated, so many degrees of freedom, you'll get some power of the particular length scale that you eliminated at the end of the day. Because I didn't quite catch the question, maybe. Right, but then I don't have a clear sense of relating it to this factor of the length scale that we want to do here. Mm-hmm. Say again. Correct. Okay. This 1.68 is a number. It just tells me as I do so many, every time I iterate, I'm going to multiply by this number. Right. So you're asking, well, why do I write it as 2 to some power instead of 3 to some power of n log something else, some other factor, right? That's correct. Okay. I mean, we can sort of come back to this. It'll become more clear later. You're right. Okay. But this kind of at least, okay. So think of this for now as a bit of a leap from here to going here to this next step here. Okay. But we are sort of asking, but at least this part is clear that I'm going to try and write down this scaling where the number of degrees of freedom is changing by an amount that's proportional to b raised to the dimension of the system. Yeah. Okay. Okay. So let's try and make this ansatz, and this was done in some ways by Vidom, Ben Vidom, and Kadanoff and others. Okay. I think it's kind of primarily driven by Ben Vidom, the idea that there can be some kind of scaling laws that we can kind of get if we make the following assumption, which is that let's assume that these factors here actually scale, all scale as some power of b of this length scale. Okay, so let's imagine, and this is not, sorry, maybe I'll erase. Is it okay if I erase this? So the idea is to say, well, let me try and use this as a heuristic, motivation for now to argue that, maybe what happens is these quantities here, for all of them, imagine that they get scaled by some power of the length scale, okay? And then let's ask what the consequences are. And later we'll kind of try and go back and see, whether this makes sense within this renormalization group framework. Okay. So let's try and do a second step, which is now to make this ansatz, which is kind of consistent with what we've seen here. But it's going to be a bit of a jump, which is to say that I'm going to have that this f, which is a function of h, t, u, whatever, okay, is going to be b to the minus d times this free energy density, except now written with h prime being the old h times b raised to some power. Okay, and just conventionally, these powers are denoted by like a little y with a subscript that tells me what is the coupling constant that's getting rescaled. Okay, so here this comes with a y subscript h. If there's a temperature, this would be some b to the power of yt. Some, what did it say? U would be some b to the power of yu. Yeah, sorry. This will be like a different transformation, like a matrix. So I mean, h could go to itself multiplied with the power of 3 plus some other thing multiplied with the power of. Correct. So in general, you're saying these need not be sort of, these look like some eigenvector type problem where I have kind of scaled along a particular direction. Let's make this assumption for now, okay? And what we'll do when we do the renormalization, in fact, we'll see that for certain cases, your eigenvectors are actually, might be mixed, as you're saying. Maybe it's along a direction that somehow mixes two of these. So the correct degrees of freedom in the vicinity are flowing along some other direction, right? So that's fine. We'll come to that. So here we are making the assumption that every quantity just becomes scaled by some factor. Okay. And what we want to do is to ask, well, what are the consequences if this is the case? Okay. So more generally, these kinds of things where a function satisfies these are called sort of homogeneous function. In other words, I take all the arguments, scale them by some factors, and multiply it by a prefactor that involves b to some power. Then I get back the same function. So these are sort of typically, what people call homogeneous functions with, so many variables or something. Okay. But here we are kind of making a connection that, okay, I can take powers of b for each of these variables, and there is a very specific dimension-dependent prefactor out here that's b to the power of this minus the number of spatial dimensions. Yeah, sorry. So this, okay, sorry. So this in the Landau theory was just the coefficient of the phi square, right? So this is a reduced temperature, which we said really comes from, I can think of this effectively as, if you want in this case, it's like saying, well, I had coupling constant divided by temperature as the relevant number. So if you want, I can think of fixing my microscopic interactions and the denominator scaling with. Right. So we are not going to, I mean, really, this is going to be a distance to the transition point. So it's not like the physical temperature is changing. It's really, how far away you are from the critical point in this Landau theory problem. Right? Otherwise, I would say that, in the lattice problem, I would sit at some temperature and maybe all my interactions will scale in some way in the lattice. All right. So with this, we want to ask, well, what are the consequences if this were to be the case? Okay. And the reason I'm kind of doing it in this order partly is because we're trying to squeeze everything into this kind of set of 2 weeks of lectures. But so let's try and use this simply as kind of a heuristic motivation to jump here already. Okay. And so now we want to ask, well, what are the consequences of this kind of form for the free energy density? Okay. So one of the things you could ask is, well, certainly we know that if these powers were positive, then these corresponding arguments are going to grow. If these powers are negative, then these arguments are going to become small. Okay. And so you can kind of try to distinguish cases where y, let's say I could be the ith argument of this function. You could distinguish 3 cases. You could say, well, I could have yi bigger than 0, where these things are going to grow. I could have yi less than 0, where they're going to shrink and vanish. Right? And I'm going to have things where yi is equal to 0 to this order. So at least to this way of doing it, it would be that nothing happens to this order. It doesn't change. Okay. And now we can ask, well, imagine I have this space of coupling constants here in my Landau theory or my Hamiltonian. I can ask, well, how is it going to change under the process of renormalization? Right. So imagine you have some high dimensional space, and I'm just drawing, something in 3 dimensions here, but in general, there's some infinite dimensional space here, right? And I want to ask, well, how do these things change for some general set of y's that I might have in the problem? And I'll say, well, for imagine you have something that's negative. Let's say along this direction, there is something where this is one of the, let's say I is 1, 2, 3, something, right? Not necessarily HB, but some set of interaction. And let's say y3 happens to be negative. Then I'll start off somewhere in this 3-dimensional space. Okay. And if y3 is negative, you'll say, well, under this process of doing this decimation or this thing, I'm going to go down. Y3 is going to, sorry, not y3. The coupling constant, whatever it is, the third one is going to decrease as I keep doing this, right? So imagine y3 is negative. Let's say y2 is positive and y1 is positive, right? Then what is it going to look like? It's going to look like I start at some point. This point tells me what is my microscopic, or in the Landau theory, I have coarse grained it a little bit. And beyond that point, I'm going to do this process, right? And it tells me that if I have to start somewhere, my initial conditions, and I'm going to watch this flow. And if I start here, this will flow down because y3 is negative, right? But eventually, because y1 and y2 are positive, this is going to go away somewhere here. Okay, sorry, I meant for this to lie in the plane. Okay, so it's going to go down to the y3 equal to, the coupling constant 3 equal to 0 plane, which is this plane. It's going to go down, but then it's going to flow away somewhere in the 1, 2 plane because both y1 and y2 are positive. It's going to go off to infinity in some. Yeah. If I start off somewhere else, it's the same story. You'd say, well, if I come here, I would kind of come down. Maybe I go off somewhere in that direction. Again, I go kind of down the plane and I kind of end up somewhere else. Okay. And now you want to ask, well, what happens if I start on this axis here? Okay. So, 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 so imagine I start on this axis. And on this axis means both the coupling constant 1 and 2 are set equal to 0 here. That's the origin. Right? They say, well, they are getting multiplied by some factor, but they're 0 to begin with, so they continue to be 0. Okay, but this axis is going to go down all the way to 0, right? So now you're going to be such that you're going to go down here and you're going to end up at this point. Yeah. Right, correct. So we'll come to that, right? So here, what I have found is that there are a bunch of things here, which is like this one here, which have flowed onto my surface, which is this 2D surface. Okay, on the 2D surface, there is a special point. Okay, and there are many special points, but in this case, I'm just highlighting one of them. There's a special point says that if I start off at that point, but off the axis, I will flow to that point. Okay, but in this space, if I deviate a little bit away from that point, then I'm going to flow off to infinity. Okay, so this looks like the analog of the critical point that we had here. Okay, so here, what did we have? We had a point, which in this case, we said I can tune the Ising model temperature and get to this value of K. If I deviate a little bit, I'm going to either flow to K equal to 0 or K equal to infinity. Okay. This looks like a higher dimensional analog of that, where if I were starting on the plane and I were sitting at this point, then this point is very special. If I sit there, I'll be there forever. It's a fixed point. But if I go a little bit away in any direction, then I'm going to flow off to infinity. Yeah. But this point is kind of special in a different way, which is that, now I can start off at a point which is not on this plane, and it will still flow to this point on the plane. Okay. So what's the meaning of this? It means that, I can start with a theory which lives in this particular instance, let's say in 3 dimensions. It has 3 coupling constants. That's what I mean. Sorry, not the spatial dimension of the theory, but the space of coupling constants. In this case, there are 3 coupling constants, right? And we are saying that of these 3 coupling constants, provided I choose 2 of them, 1 and 2, to be at this point, right? Then the initial value of the 3rd coupling constant is unimportant. Is that fine? Okay. So this tells us that, I can see how universality is now beginning to emerge in the problem, because I would say, look, imagine I have different magnets, right? They have a bunch of coupling constants, and let's imagine that there is just one extra term or something, right? Then I would have said, well, that magnet which is sitting here or sitting there or sitting there, okay, these are all magnets which are at their critical point in this, phase diagram, which has some lattice model with some bunch of interactions. That is some, let's say, material 1, that's material 2, material 3. Okay. Each of them have been tuned such that, this constant is 0 and this constant is 0. This could be, for example, temperature. This could be the magnetic field. And I have tuned T to TC, and I have tuned my magnetic field to 0, let's say, right? Then we find that the precise value at which you start off your problem may not be relevant in a very precise sense in the long distance picture. Okay, this says all these magnets, no matter whether it's material 1, material 2, all of them will eventually be flowing at long length scales to the vicinity of this point, where this particular coupling constant, the 3rd coupling constant, is actually completely unimportant. I might as well set it to 0. Is this fine? Okay. So this is an example then of some kind of a critical surface now. Okay. And under the renormalization process, I'm going to, and which we've not really done, we've kind of motivated this, I'm going to assume that certain things are going to flow to 0 in this high dimensional space, and they're going to land up on just a 2-dimensional surface at the end of the day, where most of them have vanished. Okay. And if that's the case, then I always end up, no matter where I start off in a microscopic theory, I always end up on this two-dimensional surface. But on this two-dimensional surface, I have to tune two parameters in order to sit at this critical point. Okay, so more generally, this shape, I'm kind of drawing it as if it's some, nice Cartesian kind of thing. But, in general, this is some surface and some complicated thing. It's some complicated surface. And now I have to kind of imagine I flow towards the surface. Once I hit the surface, I'm stuck on the surface. But on the surface, I have these special points where I could tune two parameters on the surface and land at that point. Okay, and that point is going to be my critical point. And if I go a little bit away from that special point, then I'm going to flow away to some different phases that might be present in the problem, like see here or here. Yeah? Okay. So this is one thing we learned from here, which is that there could be universality emerging by having a lot of these y's being negative. You could end up with a theory that looks universal. Okay. If you have too many y's that are positive, then it's not a nice thing, because imagine I end up, let's say I have some 10-dimensional space of couplings, and I find that I end up with a not a 2D surface, but imagine some 3D, subspace where all these y's are positive, right? Then in this 3-dimensional space, I have to go hunting for some special point in 3 dimensions, which means I have to tune many more parameters, in this case, 3 different parameters, in order to be able to reach the special point. Okay, so you won't be able to reach it by a simple experiments where I can tune magnetic field and temperature. I might have to reach it by, let's say, tuning magnetic field, temperature, and pressure or something like that, right? So you might have to have multiple tuning parameters that will allow us to reach these points. Okay, so in general, those kinds of points are what people call multi-critical. In other words, I want to be able to get to, I have to fine tune more to be able to reach these points. Whereas simple critical points, usually like, handful, like typically in these 2D phase diagrams that people draw, you kind of tune temperature, pressure, let's say for a fluid, or for a magnetic system, you tune temperature and magnetic field. Magnetic field is 0 and temperature you tune, and you can hit your phase transition. Yeah? Okay, very good. So what Widom kind of partially realized, and it was kind of, understood much more generally later on, was that this kind of structure is enough to say something useful about the system. Okay, which is, imagine that I have gone, and this is not the language in which Widom had thought about it at that time, because it was too early. It was kind of predating all these developments by Wilson, Kadanoff, and others, which was to ask, well, imagine somehow that these y positives, y's that are negative and y equal to 0, let me assume, I'll come back to this later. We'll look at examples of this later in one of the later lectures, is that imagine I take all the y negatives and I say, well, they have all kind of flowed to 0, and let's just throw them away because they've all gone and become 0. So I'm just going to set it equal to 0 directly here in this equation. Okay. So what you're going to get then is that the free energy, and let's do this now for the Ising case, or this kind of magnetic Hamiltonian, where really there we expect, and we'll kind of see this more clearly later, that there are only 2 relevant kind of deviations. One is going to be the magnetic field, because the magnetic field breaks the symmetry in the system. It's always some relevant perturbation in the problem. Okay. The second is going to be term which is going to be my temperature. And clearly, we know that these 2 are definitely relevant degrees of freedom for the Ising problem. Okay. And let's assume that everything else is irrelevant, as is the case, but let's assume that that's the case for now. Okay. So this entire thing, f of h, t, all of this here, I'm going to assume that all of them have flow to 0. So really, I can replace this by f of h, t, 0, 0, etc. for all of them. And that function, let's just denote it then by a function of just 2 parameters. Okay. And this one, we want to say, well, let's write it in this form now, where it's b to the minus d. These two stay, but everything else is 0 for a second. So then you're going to get b to the minus d times some f of h times b to the yh, t times b to the yt, and nothing else. Now, it turns out that if this is the structure of the free energy, it turns out you can actually say something useful about the problem, because there's enough freedom here that this B is completely arbitrary. Okay, I can use it, I can choose this factor B in order to try and pull out some of these, one of these coefficients or both of these coefficients as somehow as prefactors. Okay, so let's try. So let's assume for a second, let's say, imagine, let's take case 1 where I set the magnetic field to 0. Okay, if that's the case, then my free energy as a function of temperature is of the form where it is b to the minus d times the free energy, which is a function of this first variable is 0, the second variable is t times b to the minus yt. Okay, yt is some number which we'll calculate later. Okay, but now you say, well, b is anything. What if I choose b such that this factor here becomes just a number like 1? Okay, so if I choose a distance to the critical point, then I'm going to choose this scale factor, how much I have to go out, right? I'm going to imagine you choose t to be smaller, then I will do this, I will zoom out longer such that this product is equal to 1. Okay, if that's the case, that means I'm going to choose B, choose to zoom out by an amount such that t times b to the yt is equal to 1, or some number. Okay, 1 is just convenient. Okay, so if it's 1, then this means that I'm choosing b to be t to the minus 1 over. So b to the yt is t to the minus 1, and this product is 1. Okay. If I choose the scale factor, then I can kind of simplify this expression to be such that this b, I have made a particular choice. So this is t to the power of dimension divided by yt, right, times a function that now has no arguments left at all, right? It's just some fixed number. It's taken at some point 0, 1. Yeah. If that's the case, then you say, well, I know precisely how the free energy density scales with distance to the critical point in temperature, right? So this T here was, remember, was just the distance to the transition temperature. It had the same meaning as temperature, right? Measured in these appropriate units. So now I can start taking derivatives of the free energy with respect to temperature, right, to get physical quantities like, for example, the specific heat or the in the system. Okay, so if you do that, then you find that, oh my, I have my this second derivative here is going to be proportional to, and let me not write down the full. You would have to take derivative of this function, but this thing is going to have t to the power of d by yt minus 2. Okay. So remember what we're doing here is we are taking, so really speaking, if I have the microscopic free energy, the specific heat is really T times the second derivative with respect to temperature. Okay. But here we have assumed that that temperature, the prefactor T, is basically you've tuned yourself to the vicinity of the critical point. So the temperature derivatives are all that really matters in this example. Right? So here my specific heat is actually going to go proportional to the second derivative of this free energy density with respect to this reduced temperature. And so this tells me that I have this quantity is going to scale as a power of the distance to the transition point. Okay. So this here is going to go like, we said that, oh, in my experiments or when we did mean field theory, we found that there was some T to the power of minus alpha behavior of the specific heat. In mean field theory, this alpha was 0, right? We said, well, experimentally, alpha is not 0. Okay. But now we found that, oh, if yt had some specific value and I'm sitting in some dimension, then this particular combination, in fact, gives me alpha, right? So from here, we can read off that alpha is precisely equal to whatever, 2 minus d divided by y. It's like the gods don't like renormalization. Yeah, it's okay. It's very dramatic. Huh? I know, this is very dramatic here. Okay, so this tells us that here is a way to kind of use, we've kind of used this decimation to motivate a certain form for the free energy. But in fact, this idea was guessed at kind of long before people actually started implementing the normalization. And the idea was that if this kind of functional form was true, then we could use this functional form to try and get at critical exponents or behavior near the critical point of certain thermodynamic quantities like the specific heat. So this is, okay, this is kind of encouraging, right? And so we want to see, well, can we kind of, do other things, right? So can we calculate something else? So let's imagine I say, well, I want to calculate the spin susceptibility, or let's say the magnetization of the system, right? So if you want the magnetization, you say, well, I certainly want to take this free energy and take derivatives with respect to the field, and then set the field to 0, not set it to 0 at the beginning, right? So you say, okay, I can start with this, and I'm not going to set h equal to 0 from the beginning like we did here. But let's say I do this, and now I want to take a derivative with respect to field of this function, right? So m here is going to be proportional up to a sign is just, it's just minus df dh. And of course, I'm going to do this in the limit then that h is 0. So take a derivative and set h to 0. That's my intrinsic magnetization in the system. It might be 0 in the paramagnet and non-zero in the magnetically ordered state. And so you can say, well, let me do that here. So I would have to take, so this quantity, what is the left-hand side? So the magnetization is then going to be equal to b to the minus d. I have to take a derivative with respect to h, but let me take a derivative with respect to the first argument, right? And then take the derivative of that argument with respect to h, right? So just using the chain rule on taking derivatives. So this one is going to give me d. So let me call this a one derivative with respect to the first argument. Let me denote it as f with subscript 1 here. Okay. If I take one derivative with respect to the second argument, I'll denote it as f subscript 2. If I take two derivatives, let's call that f11, just like you denote fxx to be the second x derivative. Okay. So let's say I have to take one derivative with respect to the first argument here, and then take that h to 0. So I'm going to get 0 here. And then this t, I have not done anything, so that's going to be there. Right? But now when I took this derivative, I have to take an additional derivative of this first argument with respect to h. So that gives me a factor of b to the yh. Okay. So what we see now is that, oh, there is now a simple form where the susceptibility I have calculated as a function of this reduced temperature T. Okay. But now if I want to figure out what is the temperature dependence of the magnetization, again, we can play the same trick, which is we say that, well, you choose T, and I'm going to zoom out to some distance such that this cancels out. It's the same choice that we made here. Okay. So what we find is that the magnetization is going to scale like temperature, and here this is going to be in the ordered phase, but it's going to go like temperature to the power of -1/yt, but that is raised to this power. So it's d minus yh divided by times this f1. So this tells us, okay, what I have found is a different critical exponent. Remember that we said that, oh, this goes like mod t in the ordered phase to some power beta. Beta was the critical exponent. And what we found is that beta can be written as d minus yh divided by y. Is this fine? And now you can kind of keep doing this for other things. Right? So for example, you might say, well, why stop at one derivative? We can take one more derivative to get the magnetic susceptibility with respect to h. And if you do that, then we find that chi is going to go like, temperature so this d stays the same. Okay. The scale factor is going to stay the same. But if you take one more derivative, you're going to get one more factor of b to the yh here. And so what you end up getting is, sorry, b minus twice yh divided by. And I'm omitting sort of this thing here, but this really should have some function where now I'm taking two derivatives with respect to the first argument, dm, dh. So I have to take two derivatives. So let's call that f11 of 0, 1. Yeah. So. I would expect that, okay, magnetization will probably increase with power on both sides, which is obviously not the ceramic parameter. Correct. So I'll come to that. And yeah. So just give me one. Okay. So this tells us that, okay, what I have done is now I can also then identify that, remember we said chi goes like t to the mod t to the minus gamma, some other exponent gamma. Okay. And what we find that gamma can also be related to these quantities. So gamma is like some 2yh minus y. And you can do various things. You can ask, well, can I calculate magnetization as a function of field at temperature T equal to 0, little t equal to 0. And so you can do all that. But what you end up finding, and I'll kind of answer this question in just a second, what we end up finding is that all these exponents that we had, alpha, beta, gamma, etc., are in the end only related to these two numbers, YH and YT, that we kind of postulated here. Okay, so clearly we have only two numbers here, right? Assuming that there were two relevant things that were going to grow. Okay, and if there are two things that are growing, then we are saying that all the properties in the vicinity of this transition, such as the growth of magnetization or the divergence of the specific heat or the divergence of the susceptibility, are all governed by these two numbers. Okay, and so if that's the case, we would expect then that there must actually be relations, because remember we defined something like 6 of these critical exponents, right? And what we then expect is that, oh, in fact, there are only 2 of them that are actually independent. So in fact, there must be relations between all these different critical exponents. Okay? And in fact, historically, the relations between these exponents were kind of partially discovered, way before this, but as inequalities, where people said, well, based on thermodynamic stability, certain combinations of these exponents must be positive, or certain things have to grow faster than certain other things. So there were some thermodynamic arguments for why there might be some inequality relations between these exponents. But in fact, when Widom and people kind of postulated the scaling form, in fact, they found that a lot of these, and this was true in experiment as well, is that there are actually certain relations between these exponents directly, not inequalities, but rather equalities. Okay, and we'll come to that in a second. Okay, but to address the question that was just asked, you might say, well, I have said that this magnetization is mod T to some power, right? But I didn't tell you whether this was in the ordered phase or in the disordered phase, right? So maybe this magnetization is non-zero on both sides, right? And so really you have to think about this a little bit, because maybe what we have to do is we have to do this scaling function. Maybe we have to postulate it such that there is an F on one side of the transition and an F on the other side. Okay, such that, maybe for one of the sides, imagine let's call this an F plus and an F minus, such that F plus is for positive values of T, F minus is for negative values of T. And if at positive values of T, I set this first argument to 0, it's possible that this function vanishes. Okay, and if this function vanishes, then of course the magnetization is identically 0. It doesn't care about what the scaling form is here. Okay, so in fact, when you define these scaling functions, you have to ask, well, maybe there has to be a scaling function on the ordered side and one scaling function on the disordered side. Okay, so we have to be a little more careful perhaps in thinking about how to define these scaling forms. That's one. The second thing is, you might say, well, what if the same thing happens with the arguments? In other words, we have said that this function has some yt, yh, and so on. What if those are different for F plus and F minus? Right? Could that happen? Okay, and we'll see that we can do explicit examples where these are not different, but in fact there are some certain types of constraints where F plus and F minus, it turns out that the exponents on the two sides are the same, but the precise what people call the amplitudes in front may not be the same. So there might be some things where I have to worry about the scaling function being different on the two sides. But in most cases, basically that the exponents are the same, but the scaling functions may be different. Okay, so you have to kind of work a little bit harder than what I've kind of just done. And maybe what I'll do is kind of give you some references, maybe in light of time. Maybe that's a useful way to do this. Say again. Right. So there is you could have things where, let's say, some particular quantity might diverge at the transition, right? But if you go to a left and right, you might say, well, imagine I take the specific heat a little bit to the left of the transition, a little bit to the right of the transition. They are both very large, and let's say the specific heat is going to diverge at the transition, right? I could try and ask whether the specific heat to the right of the transition, specific heat to the left, if I take their ratio, then is there some universal number where if I go a little bit away, let's say I go instead of, let's say 1 Kelvin away from the transition on either side, let's say I go 2 Kelvin away, and I look at the ratio of the specific heats on either side, is this number somehow going to be universal or not? Right. So you could ask questions of that sort. Again, I'm not getting into that here in light of time, but yeah. So there are various, in these cases, you could have divergences at the transition, but you could have, a finite response on either side. And if you have a finite response on either side, you could ask, is the response at, let's say, 1 Kelvin above and 1 Kelvin below the transition, is there some connection between them, or is there some relation between them?
It should be continuous, right?
Yeah.
There is no discontinuity in it.
There is?
Is there any discontinuity in it?
A discontinuity in what?
Derivative of f can be discontinuous, but the functional form of
the functional form of f. So you could have like, two different scaling functions on this. So we'll look at, maybe I'll show some slides on the last where you can kind of take data from experiments and try and, do what people call like data collapse. And you can see that, there is a certain form for the function on one side of the transition and a certain form on the other side. So we will see, maybe I'll just do slides maybe in the last lecture on Friday, just showing some of this. Right. Sorry. So if the only thing you meant was the free energy has to be continuous, then yes, the free energy has to be continuous, but the form of the function on the two sides could be different still, right? So f could be continuous. So f plus at 0 might be the same as f minus at 0, but the functional forms could still be different. Okay. So is this fine? Okay. So one quick thing that we can kind of get from already from here is the following. So imagine I take, I have alpha, I have 3 of these already, right? And I could try and ask, within this, are there any constraints that, we can try and write down relations between, alpha and beta and gamma, which is satisfied as an identity because somehow I can eliminate these two numbers, YH and YT, between these 3. Okay. So in particular, you see that, that contains, these two contain YH, right? So if I try and do 2 beta plus gamma, then I will eliminate YH between these two, right? The YH gets deleted, and what you end up with is 2D from here and minus D from there, right? So this is going to give me D divided by YT, where the YH has been removed from the expression. Okay. And now you see that, I can try and remove this YT as well by combining it here. So we find that there are relations of the form alpha plus 2 beta plus gamma. If I add all 3, then in fact, all these factors of YT goes away and you're just left with this 2. So this is an example of a relation between different critical exponents, okay, that is in fact seen in experiments as well. Okay. But we can kind of see that if the scaling form holds with only 2 of these numbers being non-zero, then clearly there must be a connection between them. And one of them is this particular relation. Okay. So we can try and put in numbers. Okay. So for instance, if you do mean field theory, let me try and see where I tried to write down some numbers for this. So imagine we do mean field theory. Then of course, alpha is 0. This factor of beta, remember, was a half in mean field theory. And gamma was 1. And this relation alpha plus 2 beta plus gamma is 2 is satisfied by these mean field exponents. So if you did simple Landau mean field theory, you find a bunch of exponents and you find that they do satisfy this relation. But of course, we saw already that when compared with experiment, these Landau mean field exponents are actually incorrect. Okay. So let's say, well, what about experimental or numerical results? Okay. So let me write down sort of the thing for the Ising example here. Okay. So for the Ising case, alpha is still 0, beta, so this is in 2 dimensions. Ising example. Okay. Alpha is 0, beta is 1/8, and gamma is 7/4. So we find that, in fact, in 2 dimensions, the Ising model strongly deviates from mean field theory, right? But nevertheless, if we try and calculate this relation between exponents, then this 2 beta gives me 1/4, this gives me 7/4. So this relation still continues to. Okay. Let's do one more. I don't know if we can. Let me write it on top here. Maybe you can't see. Let's look at another case where we say, well, I'm going to take the 3D Heisenberg model. Okay. So now this has spins that are vectors that can point, anywhere in 3-dimensional spin space, unit vectors, 3-dimensional spin space. And now you can again write down what are values of alpha, beta, and gamma. So in this particular case, alpha is about minus 0.1, 0.12. Beta, I'm just writing down, is like 0.366. And these all approximate from numerics and experiment. Gamma is about 1.4. And you can try and plug in, I think it's like 1.39 something. Okay. And you can try and plug in these numbers into this relation, and you find that it still continues to. Okay. So what we learn from here is that there are certain constraints. Sorry. Oh, 3D. Sorry, this is Heisenberg. Classical, yeah. Well, okay, we expect that the thermal transition has the same exponents, but this numbers I got from just some classical. Which anisotropy? So I'm assuming it's completely isotropic for now, right? So yeah, I'm either doing the Ising case, which is purely, along Z, or I'm taking a Heisenberg model, which is completely isotropic in spin space. Correct, right? And what we find is that even though I have different models with different symmetries, here, of course, it's the only invariance was the Z2 Ising symmetry or time reversal, where everything up goes to down is a symmetry. Here, in fact, you have rotational symmetry. You take all the spins and you rotate them by the same global angle, and the Hamiltonian doesn't change. So this, in some sense, has a higher degree of symmetry than the Ising problem. We've also taken a different dimension because in 2 dimensions, there is no long range order for this one, right? But we find that, in fact, these exponent relations continue to hold despite the fact that, these are different microscopic models. These are, different dimensions. We find that, in fact, this kind of exponent relations continue to hold. Okay, and we'll come back to this in a second, but was there a question?
permitted at least interesting that essentially the directions that matter are the same for both of them.
Correct. So you could ask, well, what are the directions that would matter if I had a Heisenberg model, right? And so you might say, well, I have different degrees of freedom that I could tune. Like, for example, as Dibindu, I think, was also mentioning, you might say, well, I could take the Heisenberg model in the same spirit as the Ising model. I tune temperature, I tune a magnetic field, right? But in fact, the Heisenberg model has one more degree of freedom. I could change the anisotropy, the degree to which, let's say, the Z interaction between the spins might be different from the XX and the YY interaction between the spins. These could be different in principle. So there might be additional, variables here in that we wrote it as F of two variables, right? But there could be a third relevant, perturbation. And if that were the case, then, I couldn't stop at two variables. I would have had to include that one more. But what this tells us, in fact, certainly in the Heisenberg model, it looks like that third variable may or may not be important. I mean, here we have not broken that symmetry explicitly in this numerics. That symmetry has not been broken. So it's as if that symmetry breaking perturbation has been set equal to 0 from the outset. But you could ask, if I weakly break that symmetry in my numerics, right, then do the critical exponents change or do they not change? Okay. And it turns out that, in certain cases, this answer depends on, how many dimensions this vector has. In particular, if this is a three-dimensional, so what I'm saying is that, you could have a model where the degree of anisotropy in some sense will be defined by how many components I have. If I have only an Ising model, there is no meaning to anisotropy. If I have an XY model, I could say, well, XX could differ from YY, right? If I have a Heisenberg, you could say, well, XX, YY, ZZ could all be different in some way. So that the number of symmetry breaking perturbations in general I could add is different. Okay. But it turns out that if you have what people call a cubic Heisenberg model, in other words, a Heisenberg model perturbed by something that's relevant to a three-dimensional cubic lattice, then it turns out that, in fact, at the critical point, you can ask whether these exponents, will they change or will they do something different? Okay. So this here is where I've tuned those symmetry breaking perturbations to 0. It's the pure Heisenberg model. And then we'll say that, okay, it looks like, based on what we've done so far, that maybe I can try and describe the physics using just these two parameters. Okay. Any questions? Or? Okay. So what we seem to get from here is that, maybe there is some kind of way I want to be able to arrive systematically at this, right? We've not derived the form of this function, right? We've also not really justified the scaling, right? As was already Haridev mentioned, we have not actually pointed out, why it should be of this form. We've kind of used this real space decimation as a way to motivate this, at least for now, right? And we've said that if that's the case, and I have only two of these numbers to play with, we discover that there's some set of relations which seems to be borne out by numerics and some data, experimental data in some cases. Okay. And so now we can ask, well, is there a more systematic way to kind of formulate this without going through this kind of decimation process where there was no systematic way to kind of do this. And there was no this thing saying that, oh, if you've done this, then here is a better way to do it, or here's a systematic way to improve the calculation. Okay. And so that kind of leads us on to this idea that you can kind of, in some sense, this next step that was taken by Wilson, where, he was thinking about more generally about, field theories, right? And how to think about field theories and how to think about, infinities that people were encountering when they try and do, for example, calculations in quantum electrodynamics or calculations in other field theories. And you find that you compute certain things and they blow up. And then, you try and subtract off pieces that are blowing up. So this is the kind of way in which there was this way of thinking about the renormalization process as a way of removing infinities. And Wilson at that point had been thinking about, is there a more systematic way to define field theories? And, and this was kind of examples, the kind of examples that he and Michael Fisher applied these ideas to were things like, Wilson's work on the Kondo model, which we will not discuss, but Wilson and Fisher kind of worked on this kind of Landau theory for these magnetic transitions. And later on, people applied it to a whole bunch of other. So there are no questions here. I'm going to switch gears and then start talking about sort of this, what people call this Wilsonian renormalization. That's fine. Okay. In fact, just as an exercise, and this is given in textbooks as well, but just as an exercise, you can ask, well, what if I, instead of these 3 exponents, we wrote down a whole bunch of other exponents. So can I try and do similar analysis to try and, read off other exponents and try and sort of relate them to these 2 numbers? Okay. And in fact, there's one that I should do. So let me, before I switch gears, let me kind of do one of, yeah, sorry. Or nearest neighbor. Well, not here, right? I mean, here we have not said anything about the lattice problem. Yeah, correct. Scaling should work for long range model. We just have to ask, are long range interactions, do they induce kind of new things that become relevant, or are they going to flow to 0, right? So if I have one more parameter here that corresponds to some long range part of some interaction, I have to ask, does that become unimportant, or is that still important in the problem, right? So there are certain long range interacting models which, end up, for example, there are models of spins coupled to phonons. If you integrate out the phonons, you get some long range interaction and you get a first order transition. So the continuous transition is completely gone, right? There are some cases where, you might think, oh, long range means like all to all. And there you might think, oh, the exponent should look more mean field like, right? So depending on the range of the interactions, one could probably ask, is there something that allows me to smoothly tune critical exponent? I don't know if that's the case, right? But if you have some range of the interaction, is there a tuning parameter that lets me tune critical exponents smoothly between, let's say, these Ising exponents and mean field exponents, right? And I don't know if there are models that. Right, but are you saying they're interesting because they give you new phases, or are you saying, okay, so that's a different, okay. So if that's the case, then we have to kind of rethink this, right? Because here we are talking about the physics of, in this particular case, models which exhibit some simple order like a ferromagnet, right? If you have models where the phases themselves are different, you might have to ask, well, are the transitions between those phases described by something similar, right? So then you might say, well, not only there, it's not even a question of beginning with the critical point, right? That even the phases, the 2 fixed points on either side also correspond to something different, right? And then you have to ask, well, what is the nature of the transition between these 2 phases, which themselves are different from what we have here, right? Yeah. Is it fine? Sorry, I don't know if that's it. Sure. Okay. Okay. So actually, one thing which I should have done, before I switch gears, is an important one, which is related, in fact, to the correlation length itself. Okay, which we said is a quantity that grows as you get closer and closer to the transition point. Okay, but we never said, well, I'm going to try and derive that length scale from a thermodynamic derivative of the free energy, right? But in fact, there's a simpler way to kind of understand how that must scale, because you could say, well, imagine I give you a physical system, right? And let's say, forget about doing this renormalization or whatever. Let's say that I tell you that this physical system has a certain correlation length. So let's say I give you a microscopic setting, and I tell you that, well, the correlation length is a certain value, okay? then one way to ask is, well, how many correlated volumes are there within my entire system, right? So I could say, well, the number of correlation volumes is going to be defined as what? It's going to be defined as, take the entire system, right? This entire system is divided into little chunks of size psi to the power of d volumes. And so the number of these correlation volumes is some L to the power of d divided by the correlation length raised to the power of d. Right? You have so many correlation volumes in the problem. But now we say, well, okay, this is at some scale I did this. Okay. But now I want to ask, well, what if I were to do this coarse graining, right? And I were to do this coarse graining, then how would I find the correlation volume in the new system, right? And in the new system, you would say, well, I have, let's say, done this rescaling. Then this number of correlation volumes cannot change, right? But what is changing is that, my number of my volume of my system, or the number of degrees of freedom in my system, has now become some L to the B divided to the power of D. Right? And so I have to have some new correlation length raised to power D. So this is going to be my new correlation, number of correlation volumes, but it's basically the same number of correlation volumes. I mean, how many correlated patches you have is not changing. Okay. So if you do that, then you can kind of relate that, of course, I'm calling psi twiddle just the correlation length in my system after I've done this coarse grain, right? So what this tells you is that I have to relate psi to the d. Sorry, I don't have to, let me remove all the d's at the end of the day here, right? So what this tells me is that L by psi must be L by B divided by psi twiddle. Okay, or equivalently, my psi at a certain h and t, okay, should be equal to B times my correlation length at h prime and t prime. But h prime and t prime, remember, were h times b to the yh and t times b to the y. Sorry if I'm kind of scrambling the order. Okay, I had the field first and the temperature next, so let's kind of stick with them. So this tells us that, okay, all that happens to the correlation length is it just scales by a factor, which is just saying, well, I can have a physical correlation length, and I'm just choosing to measure it in units of my new lattice constant. And so the correlation length just scales by a simple power. Unlike the free energy density, this is a length scale. So it'll just scale with a power of the length, B itself. But from now, again, we can kind of read off what happens to this correlation length. Because remember that this continuous transition that we saw with the divergence of the correlation length only really happens when H is 0, right? So let's set this magnetic field equal to 0 in this example. So then we discover that this psi of 0 comma t must be B times this length scale of 0 comma t to the B yt. And again, we can make the same choice that this t, I can choose B such that this factor becomes 1. And so you find that this quantity is simply t to the power of, and again, I'm writing it as mod yt, but it's temperature raised to the power of minus 1 over yt. So that's this B times a correlation length, which is a function of these two variables. So you give me a magnetic field. In this case, I've set it to 0. And you give me some temperature. I have chosen a B such that this prefactor, this second argument is 1. And then we find that the correlation length scales as temperature raised to some power. Okay? And remember that this thing we define goes like mod t to the minus a critical exponent nu. Okay. So this critical exponent nu is simply given by 1 over yt. So this, in some sense, tells us that not only, alpha, beta, gamma, in this case, the correlation length exponent, all of them are going to be controlled by these two numbers. Okay. Along with dimensionality in these. So in fact, you can write down a whole host of not just the one exponent relation that I wrote down, but as an exercise, one can say, well, given that all these exponents are related to these two numbers, can I arrive at sort of all possible relations between these exponents? And maybe I'll leave that as an exercise, but you can find it in books as well. There are a whole host of these exponent identities that you can either try to derive or at least try to confirm that they're kind of what you get from having these relations. Okay. All right. So let me erase this. So maybe what I'll do, like, in the next, 10, 15 minutes is just at least set up sort of what the, this Wilsonian way of doing the problem is. And then we'll kind of, at least do maybe one step, and then we'll kind of do the remaining tomorrow. Okay, so that should be the plan. But let's try and kind of at least see how far we get. So let's again work now in the framework of Landau theory. Okay, and as I said, this is now, you can view this as an example of a field theory, where we say the partition function involves an integral or a path integral over all possible configurations of some order parameter field, phi of r, with S here, which is a functional of these order parameter fields, right? Which we said, we wrote down the form of S of phi earlier, but S of phi, in real space, we said is of the form where, it is some integral over all space of some phi square of r times some grad phi, some kappa over 2 times grad phi square, minus, in general, you could have some uniform field coupled to phi of r and so on. And of course, you could have interactions which are governed by some terms like this in the action. Right. Let's already generalize from here to the case where instead of thinking of this as an Ising model, we said for a Heisenberg, we would say, oh, these are vectors, right? Which are like a component-wise multiplication of, x, x, y, y, z, z, you kind of add them all together. So let's kind of write this in a way that already has that form. So let's write this in a slightly different form where it will be useful for generalizing from here, which is to say, I'm going to write this in the form where it is some phi alpha, where I'm imagining summing over this repeated alpha index. This alpha, sorry, I'm using alpha here. It's not the critical exponent here. It's the number of, is the x, y, and z components, for example, of the field. There will be terms which are the analog of the stiffness, which we already wrote down last time, which is that this is some di phi alpha, di phi alpha, where I now runs over space, alpha runs over the components. And the magnetic field we could assume is pointing along some direction in spin space. So let's say it points along the z direction, then this would be some phi 1 of r, for example, could be the magnetic field applied along the x direction in spin space, for example. Yeah. And now we can write down the interactions, and the simplest interaction to keep that has sort of the symmetries is one which we wrote down last time, which is just some phi dot phi whole square, which is phi alpha, then phi beta r. And we could write down other. Okay. So here alpha runs from 1 to the number of components of the spin. Right. So n equal to 1 is the Ising case, n equal to 3 is Heisenberg, but n could be something. Right. And now what we want to ask is, well, we did this kind of coarse graining in real space, but the coarse graining in real space suffered from various defects, right? One is there was no clear systematic way to do this. The second, which we already discovered, during discussions last time, was that imagine I had some complicated order, then how to do this decimation, might depend on precisely, what is the nature of the order to do this decimation. But in fact, starting from here and working in momentum space gives us kind of a much more natural way to think about the problem. Okay. So in particular, we can ask, well, how do I describe a ferromagnet in such a language? A ferromagnet is something where the phi field wants to order in a uniform state. So it's as if it's going to order at 0 momentum in this example, right? If, on the other hand, you want to have an antiferromagnet, which let's say alternates from side to side, then the ordering is going to happen at, let's say, in 1 dimension at wave vector pi, or in 2 dimensions pi pi. Yeah. And so what you see is that in the momentum space framework, what we want to do is we want to imagine that there is some Brillouin zone, right? Let's say for a solid with lattice spacing A, and let's say I take a square lattice for simplicity. This runs from minus pi by A to pi by A, let's say in both directions, or in d dimensions, there'll be some cube where every momentum has some natural extent. So there is some first Brillouin zone in which these momenta lie. Okay. And now choosing what type of ordering you have simply amounts to saying, well, where in momentum space is the ordering going to happen, right? So for a ferromagnet, you would say, well, it happens here. For an antiferromagnet, it's going to happen here. And if it's some order, some other order like stripe order or something else, maybe it happens somewhere else in momentum space. Okay. And what we realize is that certain kinds of problems, like for example, in the lattice, you might have this. If you're in the continuum, let's say you're trying to do electrodynamics or something, quantum electrodynamics or something, then really you're thinking about sort of momenta close to 0 momentum. Okay. And so in all these cases, it's useful to think about these degrees of freedom in momentum space and ask, well, can I write down this analog of what it means to do this decimation, except now doing it in momentum space. Okay. And now there's a very specific target that we want to get to at the end of the day, which is that in the end, we want to be able to describe the degrees of freedom that are responsible for the ferromagnetism or the antiferromagnetism, or it could be some other order that sits here. For example, at pi 0 and 0 pi, there could be orders which by square lattice symmetry become important at these 2 wave vectors, right? Or 4 of them, but really this is the same as that point, so I'm not writing it. Similarly, for the antiferromagnet, all these points are equivalent, right? And so now the process becomes one of asking, well, can I first isolate these regions in momentum space as the ones that I want to really focus on, right? And so for the ferromagnet, you would say, well, I want to somehow be able to zoom in progressively towards 0 wave vector. For the antiferromagnet, I want to be able to progressively zoom in towards this wave vector. And all other wave vectors are going to be essentially going to be slowly integrated out or decimated or removed in the process of zooming out. Okay, so here we would say what I want to do is for the ferromagnet, I want to imagine, let's say I draw some circle of momenta around this zero momentum. And I want to imagine that I'm progressively removing little regions in momentum space exactly as we did in our decimation problem. Except in the decimation, there was some choice. And I would say, well, I removed every other spin. You might say, well, why do that? I could have chosen something else. Here, there is a very natural target, which is I just want to end up kind of in this uniform state, which is the ferromagnet at zero momentum, right? So I want to progressively remove things which are at large momentum, which large momentum costs a lot of energy because there's a lot of twisting energy associated with that field. And so this is like costs a lot of energy. And so I would think that I want to remove those and I want to zoom in at long wavelengths and low energies as far as this theory is concerned. So you want to kind of progressively start eliminating things here, then eliminate the next shell and sort of move in towards zero momentum. If you were doing this in an antiferromagnet, you would have done exactly the same thing, except you would have said, well, let me draw a circle around this wave vector. Okay, and now start thinning out degrees of freedom, here until eventually I'm kind of zoomed in on the antiferromagnetic point. Or if I were interested in these 2 points, or for simplicity, let me kind of draw it with these two. You might say, well, I want to in fact do something that's a little more complicated. I want to zoom in towards 2 points now in momentum space where I want to do this, but at the same time, I want to do that. Right? So here, everything away from here is unimportant. And then I'm going to zoom in towards 2 of these if I want to describe a system that has ordering at pi 0 and 0 pi. Right? And this means you see that naturally, there are certain low energy fields in the problem that we have to keep, which correspond to the nature of the order that we want to describe. Okay, so for a ferromagnet, we would say, well, I just have one field, and I want to zoom in towards the zero momentum of that field. If I want to describe antiferro, you say, oh, it's also one field. It's just at a different momentum, and I want to zoom in towards pi pi. If I look at other orders, they might actually involve 2 fields. I want to have one field that's kind of focused on here, a second field that's here. And for each of those fields, I want to define a process of coarse graining that takes me towards this point or that point. Okay, so what looks like distinct momenta in this problem might end up being such that the relevant field theory that we write down may have number of fields that you keep might depend on the nature of ordering that you want to describe. Okay, so in the simplest case, that's what we wrote down here. More generally, you might have a phi that corresponds to near 0 pi and a phi that corresponds to near pi 0. So you would have 2 fields, and then you would have to write down the appropriate Landau theory using that. Yeah? Okay. So with this, now we can kind of try and write down, okay, let's do it for the simplest case and write down what this action looks like by going to momentum space. So let's define phi of r in terms of momentum degrees of freedom, right? So we will have a certain definition of what the Fourier transform modes are. And as we did before, we're going to just denote it by the same field, but with a momentum dependence here. So it's clear that that's a Fourier transform field. So I'm not using phi twiddle or something. Okay. Times e to the minus I q dot r integrated over momentum. Similarly, our phi of q is going to be defined with the inverse relation, where this is phi of r times e of r. And with this, we can kind of rewrite, we can plug this into this action, and we can write out what this action looks like in momentum space. So what is this form? So S of phi written in momentum space takes on the form where this gets replaced by a momentum integral. And let me just denote it with momentum integral here, but this is really this momentum integration with this ddq over 2 pi to the d. I'm just denoting that by the subscript q. And the terms that are just quadratic in phi look very simple. So these are just 1/2 t plus 1/2 k times q square times phi alpha q phi alpha minus q. Okay. This term here, because the field is uniform, it only couples to the total magnetization. So this one here is simply minus h times phi of q equal to 0 with the first component. Sorry. Say again. No, because one of them is q, the other is minus. Yeah, so there is a one derivative gives me iq, the other derivative gives me minus iq. So this is plus kq square. This comes from the field. Okay. And then we are left with this term, and there are higher order terms which I'm not writing down now. But this term here, we see that it has 4 powers of the field. So it has 4 different momentum integrations that will come up. But because of this one extra integral over r, there will be 3 independent momenta in the problem, and we can write down what that is, where you will get some q1, q2, q3. So now this the 3-dimensional momentum integral. There's some prefactor u, which is the coupling in front. And what you're going to get is some phi of q1, phi q2, phi q3, and phi of minus q1 minus q2 minus. And I have to remember that these came with some labels alpha, beta, and so this will have alpha, beta, and so on. Okay, and this involves, for example, higher powers of phi or powers like higher gradients involving del square phi whole square in terms of that sort. All of them are kind of clubbed together. I've not written it out, you can kind of write it. So what we want to do, and maybe we'll kind of, sorry, it's over time. So what we want to do now is to kind of take this and do this process of separating it into modes that are close to the origin and modes that are far away from the origin. And so it's natural to define in this language what you might call modes that are slow and modes that are fast. Okay. And by slow, what we mean are modes that have a momenta that are smaller than some value, and modes that have momenta that are larger than some value. Okay. So you might say, well, what should I keep? And a natural thing to do is to kind of imagine that I've replaced my square Brillouin zone by imagine a circular zone with the same area. They might say, well, I know that there is a total maximum momentum that's there in the solid, which is set by the spacing between the lattice points in real space, right? And so these fast modes are going to be modes that run over, things that are close to that, maximum momentum. Slow modes are going to be those that are closer to 0. Okay. But we can kind of do this by first defining sort of what the limits are on this momentum integration, right? So here we were integrating over some square lattice, for example, we would have had some momentum integral. but we could equally well replace it by sort of an integral over a circular Brillouin zone effectively. And that Brillouin zone momentum will have some radius that we will call capital lambda. And this lambda is what people call an ultraviolet cutoff in momentum space. Okay? And so the slow modes and fast modes now are going to be defined such that it is going to be defined for momenta that lie between 0 and some fraction of this cutoff. And fast modes are going to be defined by momenta that lie between this value and the upper cutoff. So we're making the separation between things that might be here and things that might be here. Okay. And now what we want to do is progressively kind of zoom towards the center, which means progressively increasing the value of B, such that eventually the slow modes only encompass things very close to 0 momentum, and the fast modes is going to be everything else in the. Okay. So what we'll do tomorrow is we'll kind of use the slow fast separation and write out in 2 steps. We'll kind of write out what these do when we kind of try and decompose this action into things that are slow and things that are fast, and how this interaction here will lead to kind of mode coupling that will become important and will give us kind of the nonlinear terms that will be responsible for driving this renormalization. Okay, so we'll do that tomorrow. Sorry. Correct. Correct. And in particular, if Q naught is like, for example, here and there, then we would have to introduce 2 fields, because I want to be able to zoom in, but I can't zoom in towards both these fields with a single, both these momenta with a single field, right? Because if I keep a single field, then I say, well, how can I zoom in towards here? Because it looks like I should have one patch here and one patch there. So in fact, it's better to then say that, oh, my order parameter actually is composed of 2 fields, one near pi 0, one near 0 pi. So my Landau theory will be written in terms of 2 fields, phi 1 and phi 2. And I would have to kind of write out this theory in terms of these 2 fields. Well, not just that, because in some, right. So part of the reason is, when you do this real space, we found that, it's not a very clear picture for how to systematically do these calculations in real space. Okay. Here, there's a slightly better picture because I'm kind of zooming in towards the relevant kind of uniform state, right? Without relying on some specific approximate way of removing certain degrees of freedom in the problem, right? I can, I chose to remove like every second side, but you might say, why not every third side, or do something else like we did in 2 dimensions? There's no clear, prescription that this is better or that is better. Here, really, we understand what we're doing in the sense we are kind of slowly zooming in from things that cost a lot of energy or cost a lot of action to things that actually correspond to the critical modes in the problem, which are at this momenta or that momenta. Yeah. Mm-hmm.
This sort of assumes that the low energy state is local in the state. Something like parameter of oscillator not local in
Oh no, why are you saying it's not local in momentum space for that? Because this is an insulator, but of some magnetic insulator we are thinking of. So are you thinking of like fermions or? Okay. Correct. So there we would have to ask, well, in a Mott insulator. So imagine I have a Mott insulator. You would say, well, in an insulator, I don't have any charge degrees of freedom. I want to be able to describe my spin degrees of freedom. And now you could ask, well, how are the spin degrees of freedom going to order? And they might have this physics, for instance, right? But more generally, a challenging problem is, imagine I don't have points in momentum space, but rather I have extended regions in momentum space, right? So for fermions, you might say, well, what if I have a Fermi surface? Or even in magnetic models, there are examples of frustrated models, which Dibyendu was briefly asking about, where if I tune some first neighbor and second neighbor, third neighbor, and if you have, let's say, triangular geometry or some of these lattices, it turns out that you get entire lines in momentum space, which cost very little energy. Okay, so the ordering happens on, what looks like surfaces in momentum space. And then you have to say that, oh, well, I have to define my RG procedure has to be such that I'm going to zoom in towards that line or towards that. And those need, what people call these kind of functional renormalization group ideas going beyond this. And maybe I mean, a simple one is in this disordered spin chain, but the idea is that, you're not thinking about now a single point in momentum space where I'm interested in the interactions or these effective interactions. There's a whole slice in momentum space where I'm asking about effective interactions. And so these interactions themselves become functions of momenta, and that entire function will get renormalized as you go through this process. Okay, so you have to do what people call this functional renormalization group. In those cases, it's important to. Yeah. Okay, so stop here. I guess maybe there is tea outside.